Well, it's convenient that I'm going right after Andy because I can give you all some good context for why we implemented this EMBESS feature in Psi4 and what we're starting to do with it. Oh, and by the way, I'm a grad student in David Sherrill's group. So a lot of the research that we do revolves around using Psi4 to calculate non-covalent interactions. And particularly when we work with people like our collaborators at Bristol Myers Squibb, we're interested in calculating these NCIs for really big systems like protein ligand complexes. We can do that with Psi4, but when we want to do this for many, many complexes, like if we're looking at how a ligand fits in a protein pocket or screening many ligands, it's not really possible with any quantum chemistry. So we've been exploring some alternate pathways to approximate these non-covalent interactions and do so as accurately as possible. The first way we started out doing this is instead of trying to calculate the NCIs directly, we develop data sets of dimers that are representative of the ligands and proteins that we're working with, and also a good bit smaller. We calculate NCIs for those, and then we use some sort of machine learning model, neural networks usually, to make a model of the interaction energy. So then we can predict on the larger system at a much cheaper cost. We've done this a couple different ways and had some really good results. One thing we did notice, though, is these models tend to have some weaknesses at the very long ranges and strangely don't do very well at predicting long-range electrostatics when that happens to be sort of one of the easiest things to model classically. So with this EMBESS code, we've started moving over to seeing how we can structure these models where instead we create data sets of monomers, predict monomer properties, which are electron densities, charges, dipoles, quadrupoles, and then using those properties and some sort of ab initio force field, go ahead and predict the NCIs that way. And that has a lot of benefits that the sort of bottom pathway doesn't have. And I'll be talking a little bit about how we've gone about making those models. So like I said, you need a big data set of monomers. Here's a representation of what we came up with. We have about 50,000 monomers, all calculated and run with Psi4 DFT. They are all organic or drug-like monomers. They have all sorts of rings and bonds and atom types and should be pretty representative of any ligand we might see in a protein-ligand interaction. Next, with this EMBESS code, we can take the molecular density that Psi4 calculates with DFT, partition it into atomic densities, and then those atomic densities are represented with a multipole expansion. So we save the monopoles or partial charges, the dipole vectors, and the quadrupoles, and we have one of those for each atom. And with those values, we can get a pretty good approximation of the electrostatics between interacting molecules, especially at long range. So our machine learning method of choice is these message passing neural networks that are pretty new. And if you're not familiar with them, I definitely recommend looking into them. They're really appropriate for modeling chemical data, and they have people have shown that they do really well on a number of problems. So I won't go into how they work really here, but I will tell you that on this test set where we trained our message passing neural network on a bunch of EMBESS multipoles, we can predict multipoles on atoms in molecules that the model has never seen before with very high accuracy. So in each of these graphs, the x-axis is the value that is computed with EMBESS, and the y-axis is the value predicted by the message passing neural network. And again, keep in mind that this is a true test set. So these are atomic or atoms that the model has never seen. So we can get these really cheaply and really accurately. I can now show you an example application of where we might use this. So in this graph, I have a trajectory of the aspirin molecule, which is visualized here in the lower left. And for this carbon right here, I went and at each step in the trajectory, calculated what the charge of that carbon would be with EMBESS, and that's shown in red. So because this carbon in the MD simulation, which is at a high temperature, the bonds move around, the angles bend, the torsions rotate, the charge, according to this partitioning, changes. And when we throw our message passing neural network at this system, you can see in the dotted blue line that we can actually capture most of these conformational dependencies of the carbon's charge. And you can contrast that with a black line, which would be just the charge if we use the optimized aspirin geometry. So being able to predict these atomic properties really accurately and really fast might be a super interesting way of doing force field parameterizations, or maybe doing some sort of on-the-fly parameterization. And I should also mention that aspirin was not in the training set at all, and actually the training set had only equilibrium geometries. So predicting out of equilibrium geometries is sort of a new task for this model. Moving on, really briefly, we can compare the electrostatics that we get by using these EMBESS multipoles with Psi4 electrostatics, which we can think of as sort of a more accurate QM electrostatics that takes into account charge penetration. So here I have a doubly bound hydrogen dimer, and as I pull it apart, past maybe 5 angstroms, the electrostatics that I get with a quantum mechanical based method like SAPT exactly matches the classical ab initio electrostatics using my machine learned multipoles. And I will leave it at that. Thank you all.